Okay, so today we'll look at the series circuits, which is the idea of a little more complex circuit where you have more than one element, so more than one resistor, more than one light bulb, but there's still only one path. And that's put certain restrictions, and then we'll use just simple laws like law of conservation of energy and charge to kind of work out what are the basic rules for the things that we don't already understand about these circuits. So first, let's draw just a very simple diagram. I'm going to draw it in the American style. And we'll place 3 resistors, but this applies to essentially having at least 2 or more resistors before you're going to run into any problems. So that is to say, if there was only one resistor, then we really wouldn't have any problem with this because the circuit would be, it would still be series. It would still only have one path, but we've already learned the rules to be able to take care of that. So the problem is, what do you do when you have more than one resistor in there? So there will be some voltage and some current. I will refer to those as Vs and Is because that is the source. The battery is the source of all of the energy in the circuit. Everything that happens in the circuit is happening because that battery is supplying that energy. Batteries are essentially supplying that through chemical energy, but of course the energy can be supplied through other ways. So the power plants may be supplying that energy, and everything still works exactly the same. So with the resistors, we would have each resistor has some resistance to it. And also each resistor, as the electricity passes through it, uses up some portion of the energy and then allows some of that energy to continue on. It must, because if this guy used up all of the energy in the circuit on the first resistor, then obviously these guys would receive no energy at all. So each of these resistors has a current that passes through it. And the most obvious thing that we can all see is that obviously these currents must all be the same. So that is to say that if I imagine the I1, I2, or I3, those would all be the same as IS, the current that is going through the battery, because there's no other path. So that's not even really like a physical law or a principle. It's just really more an acknowledgement of reality that there is nowhere for the current to go. So if 1 amp passes through this corner, then 1 amp must be passing through every place on this circuit. Otherwise, charge would begin to build up. That would be a violation of conservation of charge. So the idea of conservation of charge is simply that you can't create charge, you can't destroy charge. You can just move it around and you can transfer it from one object to another, but it's not created or destroyed. So if 1 amp passes through this corner here, but then over in this corner, we're only getting half an amp, then obviously we have half an amp worth of charge, which has disappeared somehow and does not have any place to go and yet is not in the system. So one of the most basic rules, which is just, I would say common sense, but I will use a physical law, is that the current that you find passing through the battery, which is our source, is equal to I1, but that would also be equal to I2, and then also I3, and that is due to conservation of charge. So that is the explanation about why the current must be the same everywhere within a circuit, a series circuit. Okay, well, here's the thing. The battery supplies all of the energies for the charges that pass through it. So the voltage on the battery is essentially going to be shared because each of these guys will get some portion of that energy. So imagine that we sent 1 coulomb around of charge, and this is, let's say it's a 12-volt battery. So every coulomb of charge that leaves this battery carries with it 12 joules worth of energy to deposit in the different resistors. But the question is, how is it distributed? What proportion of it goes to this guy compared to this guy compared to this guy? So these voltages, V1, V2, and V3, it must be true that these voltages will add up to the voltage from the battery because the battery is supplying all of the energy. So that would be a violation of conservation of energy. If the battery supplies 12 joules for every coulomb of charge that passes through, then by the time it gets through all of these guys, it has to be back down to 0. It has to have expended all of that energy in order to be able to come back to the battery and be re-energized. Otherwise, as we pass through, the voltage would just continue to increase. If there was energy left over, or if there was energy missing, then we would have a different voltage than we would when we pass through the battery. So the first time the charges come through, they're at 12 volts. And if they come back and they still have, let's say, 2 volts, then when they pass through here and gain that 12 volts again, now they're at 14. Somehow they're gaining energy, even though there's no source from the outside other than the battery to provide that energy. So this statement that the voltage of the source is equal to V1 plus V2 plus V3 plus whatever other elements are in the circuit, what other resistors that you see in the circuit. And that is due to conservation of energy. And these are two of the most foundational conservation laws. In fact, I would say easily the two most fundamental. Some conservation rules, there are other conservation rules that are also very clearly not violated, but these are the two that we don't see examples of any violations, and they have profound effects on what we see in the world. The fact that these two things cannot be created or destroyed, they only get transferred from one object to another, or in the case of energy, it gets transformed into some other form of energy. So now we're going to put all of this together. We know that the currents are the same everywhere, and that we know that the voltages must be shared, because this we're talking about the energy. So we must satisfy conservation of energy. Whatever is giving energy to the system, the other guys must be taking that energy away, so that no energy is coming in or out of the system except for that's coming from the battery. So if you remember, that V is equal to I times R, then we can take this equation and let's rewrite it, but let's replace it with the various things that we would replace in terms of current and resistance. So on this side, it's going to be IS times R, and now we're going to give a name for this thing. Now, in different books, you'll see different things. Some say the total resistance or the net resistance. But I'm going to use EQ, and the reason why I want to use that is because it is the equivalent resistance. So in other words, if we could take these three resistors and get rid of them, what one resistor would replace them and the battery would never be able to tell the difference? That is the resistance that the battery is facing. And I really want to point this out because the battery doesn't know what it's connected to. The battery just has a wire connected on one end and a wire connecting the other. And the battery can feel how difficult it is for the charges to move. So the more difficult that it is for the charges to move, the less charges it's going to be able to push out into the circuit. So this equivalent resistance is not something that's internal to the battery. It actually doesn't have anything to do with the battery at all. It is simply the resistance that the battery feels when it's connected to this whatever combination of resistors you have. So let's add this guy over here. Those are the properties. Now, again, the voltage and the current are the properties of the battery. The REQ is not a property of the battery. It's simply the equivalent resistance that this circuit would produce if we could replace it with a single resistor, which is essentially exactly what would happen. If we replace all three of these with one resistor called REQ, then how would we get the voltage on the battery? Well, it would be I times whatever the value of that resistor was. So what we're going to do on the other side is replace each of the individuals, V1, V2, V3, with their equivalent. So I1, R1 plus I2, R2 plus I3, R3. Now, because we already established that we know that the currents are going to be the same everywhere, we can essentially just cancel these guys out, and whatever remains is the rule for equivalent resistance in a series circuit. So this is going to be R1 plus R2 plus R3 plus whatever number of resistors that you have. So there's no limit to how many that you would have. Obviously, there would be at least two, because if we have only one, then we don't need to go through all these rules. But if there's more than one resistor, then you're going to add them all up to get the total resistance of the circuit. So let's take a look at an example, and that will hopefully help to make it a little bit more clear. So I'll redraw the same circuit, a little bit bigger this time, because we're going to be putting some labels, and there'll be quite a few numbers. Okay, so let's say in this example that the battery is a 12-volt source. And for each of the resistors, we're going to keep the numbers nice and simple. So we'll have a 5-ohm resistor, a 10-ohm resistor, and a 15 ohm resistor. Okay, so, oh, I'm so sorry. So this is the issue with the circuit. What we're going to do is we're going to simplify this circuit down until we have only a single resistor, and then we're going to start working our way backwards through those circuit diagrams until we have everything filled in. And what I mean by that is, what I want to do is I want to solve this circuit. And if you were asked to solve the circuit, it would mean to know everything about the electrical properties, the big three: the voltage, the current, and the resistance. I would like to know those for each of these three guys. Now, realistically, I'm not going to get the internal resistance for the battery. That's a little bit more subtle. We might look at that later. But what I do want to be able to see is that there is some equivalent resistance that these three could be replaced with. And by simplifying the circuit down, that's going to allow me to figure out the current that came from the battery. And once I have that current, that's going to help me to go back, because remember, all these guys have the same current. So once I work out what the current of the battery is, then I can start going back and piecing together what were the details, what are some of the missing details about how these guys broke down. And then we'll verify that these rules actually work. So what we're going to kind of do is go a little bit in reverse. I'm going to start by trying to calculate the equivalent resistance for this circuit, which simply says that Req would be equal to 5 plus 10 plus 15 to give me 30 ohms. And what essentially that is saying is that if I took those three resistors out, the 5, the 10, and the 15, and I replaced them with a single resistor that had a value of 30 ohms, then the battery would never be able to tell the difference. To the battery, that's exactly the same circuit. The same amount of current's going to flow, same amount of energy is going to be dissipated. It'll just be done with a single resistor instead of with 3 resistors. So this is our equivalent resistance. Excuse me. And now what we're going to do is try to start figuring out what happened to the battery. But in order to do that, I'm going to redraw the circuit. It's a little bit simpler this time, though. I still have my 12-volt battery, but now this time Req is equal to... Oh, it's a terrible example of how to draw that. So we have the equivalent resistance and the voltage of the battery, and that is going to allow me to figure out IS. Because I know that the current, let me go back up to this formula, the current in any one of these elements would be equal to the voltage of that element divided by the resistance. So I could say that Vs divided by Req. So that was 12 volts divided by 30 ohms to give me 0.40 amps. And now in terms of the current, we're done, actually. We've calculated all the currents for all three of the circuit elements because they all have the same current. So just to emphasize it, I'll say I1 equals I2 equals I3 equals 0.40 amps. Okay, so we have all of the currents for all of the resistors in our circuit. And we also know the voltage on the battery, and I know the equivalent resistance. I could write that down, the Req, which was 30 ohms. So that only leaves for us to figure out what was the voltage drop, how much voltage was used by each of those three circuits. So at this point now, I'm done with this diagram. I don't need this diagram anymore. Because remember, this doesn't actually exist. This was just to get me to the point where I could at least figure out what's coming from the battery. What kind of current is coming from the battery. Now that I have that current, I'm going to go back and start filling in the details. And let's take a look at, remember, V is equal to I times R. So V1 would be equal to I1 times R1. And that would be equal to 0.40 times 5. V2 would be equal to I2 times R2, 0.4. Remember, the current's the same everywhere in a series circuit. And lastly, V3, which is I3 times R3, 0.40 and 15. Okay, well, 0.4 times 10, that would be 4. And this must be half of that. And this guy is going to be, if you put it in your calculator, you'll see that it says 6 volts. So in resistor 1, the voltage dropped by 2 volts. In resistor 2, it dropped by 4. In resistor 3, it dropped by 6. If we add up, what's the total of all these voltage drops? exactly what the rules say, and that is that the voltages should all add up to be the voltage of the battery, and that's exactly what happened. When I added up the individual voltages, they added up to the voltage of the battery. And this is the approach that you'll use in all of the series circuits, or if there's a small section of a circuit that is series, you'll continue to follow those rules to go ahead and determine the equivalent resistance as a way of figuring out what the current from the battery is. And once you have that piece of information, then you'll be able to go back and start filling in all the details for the missing pieces of information.